This is a recording of Chapter 4 from the book Electricity and Electronics by Garish, Duggar, and Roberts, edited and narrated by Hector Bello. Again, Chapter 4, Energy. An understanding of electrical power will enable you to select the proper size components needed to build or maintain a circuit. All electrical circuits convert electron flow into some form of energy, such as heat, light, or mechanical energy, magnetism. Many industrial systems are custom designed. They are one-of-a-kind or prototypes. These systems must be laid out according to predetermined loads. Once the amount of power is required is determined, we can easily calculate such factors as conductor and fuse size. 4.1 Work and horsepower. Work is force applied over a distance. Work is expressed in units such as foot-pounds or inch-pounds. For example, if a 10-pound weight is lifted 1 foot, the work accomplished equals 10 foot-pounds. See figure 4-1 on the screen. Look at the formula F times D equals work. If F is the force in pounds and D is the distance in feet, the work is calculated in foot-pounds. 10 pounds times 1 foot equals 10 foot-pounds of work. It is important to note that no reference is made to the time when calculating work. It may take 5 seconds or 10 minutes to move the 10 pounds to 1 foot in the example. Power. Power is the amount of work done based on a time period, such as seconds or minutes. Power is the time rate of doing work. In the last example, 10 pounds was moved 1 foot with no time restrictions. If the same 10 pounds were moved 1 foot in half a second, or 0.5 seconds, the power expended would equal to 20 foot-pounds per second. The formula for power, screen, which is power equals work divided time, or force times distance divided time. Horsepower is used for stating mechanical power. Again, horsepower is used for stating mechanical power. Electrical machines such as motors are rated in horsepower. 1 horsepower, or HP, is defined as a work rate of 550 foot-pounds per second. Also, 33,000 foot-pounds per minute equals to 1 horsepower. In electricity, the unit of power is the watt, capital W. It was named in honor of James Watt, who is credited with the invention of the steam engine. When 1 volt of electrical pressure moves 1 coulomb of electricity in 1 second, the work accomplished is equal to 1 watt of power. Recall the definition of the ampere, the movement of 1 coulomb of electrons past a given point in a circuit in 1 second. Thus, power is an electrical circuit. Power in an electrical circuit can be written in terms of voltage and current. The formula for electrical power is on the screen. Capital P, or watts, equals capital E, volts, times capital I, amperes. P equals E times I. To convert electrical power in watts into mechanical power in horsepower, you can use the following conversion factor. 746 watts equals 1 horsepower. The power, sometimes called Watt's law, can be arranged algebraically. If 2 quantities are known, the third third unknown can be found. Use the device in figure 4-2 to help memorize the following formulas. Here's the device. A memory device to help solve the power problems. Cover the unknown quantity and the remaining letters give the correct equation. For example, if E is unknown, cover E and P over I or P divided I remains. Thus, E equals P divided by I. Example. A circuit with an unknown load has an applied voltage of 100 volts. The measured current is 2 amperes. How much power is consumed? In this problem, power equals current times voltage. Again, power equals 2 amps times 100 volts. Thus, power equals 200 watts. Example 2. Second example, an electric toaster rated at 550 watts is connected to a 117 volt source. How much current will this appliance use? Again, I equals P divided E, or P over E, or current equals power divided voltage. So current equals 550 watts, according to the problem, divided 117 volts. Thus, current equals 4.7 amps. Lesson in safety. An electrical current produces heat when it passes through a resistance. Heaters and resistors will remain hot for some time after the power is removed. Handle them carefully. Burns should be treated immediately. See your instructor. At this time, please perform review questions for section 4.1. Ohm's law and Watt's law. It is possible to combine Ohm's law and Watt's law to produce simple formulas that permit you to solve for current, voltage, resistance, or power if any of those quantities are known. In figure 4-3, these equations are listed with an explanation of how they are created from the two laws. These formulas can be arranged in a wheel-shaped memory device for ready reference. Refer to figure 4-4 shown on the screen to use this device. Find your unknown quantity in the smaller center circle. This is the left half of your equation. Next, choose one of the 3 variable combinations in the outer circle that falls in the same quarter of the chart. As your unknown quantity, choose the variable combination that uses 2 known quantities in your circuit. This becomes the right half of your equation. For example, if you're given a situation where the current and resistance are known and the power is unknown, find the P in the upper left corner of the center circle. Then find the variable combination that involves current and resistance, the middle combination of the 3 choices, or current squared, or to the second power, times R. Thus, your final equation is power equals, or P equals, current squared, or to the second power, times R. So, plug in your known values and solve for the power. Figure 4-3. This table states a variety of basic formulas that are needed to solve problems. At this time, please review questions for section 4.2 and perform those as well. Page 78. 4.3. The wattmeter and watt hours. Power is an electric circuit. Power in an electric circuit is equal to the product of the voltage and the current. To devise a meter that measures watts, a movement similar to the D'Arsovall movement can be used. The permanent magnetic field found in the D'Arsovall movement, however, is replaced with coils from an electromagnet. This type of meter is referred to as a electrodynamometer movement. A circuit diagram of a simple electrodynamometer movement is shown in Figure 4-5 as shown on the screen. This arrangement creates a wattmeter, a meter that measures the instantaneous power. A moving coil with the proper multiplier resistance is connected to cross the voltage in the circuit. The coils of the electromagnet are connected in series with the circuit under measurement. The action between the two magnetic fields is proportional to the product of the voltage and the current. The flexion of the indicating needle is read on a calibrated scale in watts. Figure shown on the screen, diagram of a wattmeter. While wattmeter measures the instantaneous power used in a circuit, a watt-hour meter measures the amount of power used in a given time. It is installed by the power company on the outside of your home or business. Since watt-hour is a very small unit, the standard utility meters read kilowatt hours or 1000 watt hours. The number of kilowatt equals voltage times resistance divided by 1000, or E times I divided by 1000. Electric power consumed is purchased at a rate per kilowatt hour. The watt-hour meter is a complicated type of induction motor. It uses field coils in series with the line current and also field coils connected across the line voltage. An aluminum disc rotates within these fields at a rate proportional to the power consumed. The disc is geared to an indicating dial. The dial shows the amount of power used. To read the watt-hour meter, see Figure 4-6. Dial A on the right reads from 0 to 10 units of kilowatt hours. For each revolution of dial A, dial B advances 1. For each revolution of dial B, dial C advances 1. For each revolution of dial C, dial D advances 1. Mathematically, dial A represents units of 1, dial B represents units of 10, dial C represents units of 100, and dial D represents units of 1000. Figure 4-6, as seen on the screen, is the kilowatt hours. Indicated equals 4,255. When the dial indicator rests between the numbers, the lower number is selected. Be careful when reading the meter. Note that 2 of the dials read clockwise, A and C, and 2 of the dials read counterclockwise, B and D. This arrangement is because the gears of the dials are connected directly to each other. Read the meter illustrated in Figure 4-6. The dial A points to 5, dial B points between 5 and 6, dial C points between 2 and 3, dial D between 4 and 5. Therefore, the correct reading would be 4,255 kilowatt hours. Notice that when the indicating arrow is between numbers, the lower number should be used. At times, it is difficult to determine if the arrow has reached the number to which it is pointing, or if the arrow has just approached that number. To make your determination, look at the dial immediately to the right of the dial in question. If the arrow on the dial to the right is between 9 and 0, then the number is still the lower value. If the arrow is past the 0, then the number is the larger value. Use Figure 4-7 as an example. The arrow in dial D appears to be pointing to the number 4. To determine if it is a 4 value or still a 3, look at the dial immediately to its right, dial C. Dial C has not quite reached 0. It is still between 9 and 0, thus the dial is actually still a 3. To practice reading meters, why not read the meter at your home each day for several days and compute the power used? The power consumed is found by subtracting the previous reading from the present reading. The difference between the two readings is the number of kilowatt hours used over the length of time between the two readings. At this time, please review questions for section 4.3 at the bottom of page 79. Efficiency. Efficiency can be best defined as a ratio of electrical power. This ratio is a comparison of the input power to the output power of the device. Efficiency can be expressed as a percentage or efficiency equals power out divided power in times 100. In the previous chapter, the efficiencies of electric lamps were determined by comparing their input powers in watts to their output light in lumens. The more output in lumens per watt, the more efficient the lamp. Most electrical equipment compares the input, volts and amps, to the output power, which can be volts and amps, watts, or horsepower. To determine the efficiency of a DC motor, the input power is compared to the output power. Look at figure 4-8. A 12-volt, 1 horsepower DC motor is connected to a 1 horsepower mechanical load. Compare the input power to the output power, multiplying the input voltage, 12 volts, times the input amperage, 90 amps, gives the input power rating of 1080 watts. The output power of the motor under a mechanical load equals to 1 horsepower, 746 watts. Dividing the output power, 746 watts, by the input power, 1080 watts, gives 0.69. Multiplied by 100, the efficiency is 69%. Energy efficiency rating. The federal government tests products to ensure that the energy efficiency rating, or EER, is correct. Electrical appliances are required to display their EER on their product label. EERs are expressed as a percentage. The higher the percentage, the more efficient the unit. The more efficient the unit, the cheaper it is to operate. Manufacturers of equipment such as heating, cooling, cooking, and other appliances have designed electrical systems for operation at peak efficiency. Many times it is the technician's responsibility to determine the best equipment to purchase. When selecting equipment, it is important to consider cost efficiency and operation as well as the actual purchase price of the product. When choosing an electromechanical device, such as an electric motor, lighting system, air conditioning unit, or welder, consideration of the operational cost is critical. Determining the efficiency of the equipment can save the owner thousands of dollars over several years of use. Gears, power. By using gears and pulleys in an electromechanical system, we can manipulate factors such as torque, work, and RPM while maintaining the same horsepower. Figure 4-9 shows a motor with pulley A, which is connected to pulley B. The ratio of the circumferences of these two pulleys is 3:1. This means that pulley A must make 3 complete revolutions for pulley B to complete 1 revolution. This also means that the two pulleys have 3:1 speed ratio. Once this ratio is known, it is easy to find the speed and work ratio between the two pulleys. The study of physics includes the law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed. Energy can only be converted from one form to another. In the pulley example, the energy or power of pulley A is equal to that of pulley B, with the exception of a small energy loss due to friction. Look carefully at the ratio of the pulleys in the example. While their speed of pulley B is decreased, it is torque, the twisting force, that is increased. Using this pulley setup, it is possible to move great weights long distances with a relatively small motor. However, the time period it takes to move the weight is increased. Look at figure 4-10 shown on the screen. The speed of pulley C is 1/3 the speed of pulley B and 1/9 the speed of pulley A. The speed in this example has been reduced 9 times from pulley A to pulley C. The torque has been increased 9 times. This 9-fold increase in torque is how it is possible to move extremely heavy loads with a relatively small motor. Note the fact that the horsepower will be the same throughout the mechanical system, even though the amount of work has changed. To avoid the safety problems associated with pulleys and chains, many applications use gear reducers to obtain great twisting forces. Gear reducers lower the RPM of the gear reducer shaft. See figure 4-11 shown on the screen. Gear reducers with a ratio of 50:1 or higher are common. At this time, please perform review questions for section 4.4, bottom of page 81. After that, please perform summary reading. Summary reading. Work is equal to force times distance. Power is the time rate of doing work. Mechanical power is measured in horsepower. Electrical power is measured in watts. 1 horsepower is equal to 746 watts. Again, 1 horsepower is equal to 746 watts. Watt's law is a mathematical formula stating that relationship of power, voltage, and current in a circuit. It is P equals I times E, or power equals current times voltage. There are definite relationships between Ohm's law and Watt's law, as shown in figures 4-3 and 4-4. Please review. A wattmeter measures the instantaneous power used in a circuit. A watt-hour meter measures the amount of power used in a circuit over a period of time. Efficiency is expressed as a percentage and indicates how well one form of energy is converted to another form of energy. Efficiency is equal to the power out divided by the power in. The amount of work done can be manipulated by gears and pulley systems while maintaining the same horsepower. The law of conservation states that energy can neither be created nor destroyed. It can only be converted from one form to another. End of chapter 4. You have achieved the rank of corporal, rank number 4. Congratulations.